by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody! I hope everyone's having a beautiful day. I want to welcome you onto the stream today. We're doing it a little earlier here today as per our usual time. Usually we do this in the early afternoon here, but I thought we'd do it a little earlier seeing as today is Valentine's Day. Happy Valentine's Day! That's another reason why I'm doing it at this time as well, as I know some people would prefer to do something in the evening or maybe have some other plans, whether you're doing it on your own or you're with a couple or you have somebody that you love very, very much, whether it be your family, whether it be someone special. I want to make sure you at least have some time to go do that, okay? So that's why we're doing it a little earlier today. And also at the same time, I thought I would try a little earlier as well. So a couple quick things before we get started. I just need to make one important remark, is if you hear any loud squealing noises or crying noises, is because we have a puppy in the house, like near the studio here. And she's still learning, and she's right now in a playpen. So just need to note that if you hear any barking from a little high-pitched bark, don't worry, she is in very good hands. She's just in her playpen. But the thing is, I can't just bring her down here because she's just a little puppy, and I worry about. She's right now doing potty practice. She's just learning about this stuff. So I gotta make sure that she's somewhere where she knows she can go use the washroom, but at the same time isn't gonna disrupt the lecture too much. So I just need to mention that. So don't worry if you hear any loud, high-pitched noises. Don't worry. She is all okay. Okay, don't worry about it. It's all good. But yes, she is very, very cute. Very, very cute. So, anyways, other than that, I also have to mention, I have posted this link on social media, but I want to know your availability for best calibrating our schedule for the upcoming months. So please fill out this questionnaire. It's helpful information for us to know when you're best available so that when we do our live shows, whether it be the live lecture like this, or it's our gaming or entertainment shows, that they are in fact something that you can come and watch. I just want to, because the people that do come, it's just the problem is that I know everybody's got all sorts of different things they're doing, and I know that changes over the year. So I usually like to get an idea of what everybody's up to. But yeah, no, so last thing before we get into today's lecture, so note that if you have any questions during the lecture, please put them in the chat. I will address it. Likewise, if it's something a little bit more complicated, most certainly will come to it when we get to about an intermission between two topics. But if it's something smaller, I can address it right on the fly. So also, for those that need to know this, just in case, is that if the chat is visible on the screen, text-to-speech will play through on, for example, Twitch. For some platforms, it won't. But I just need to acknowledge that just because the chat isn't visible on the screen doesn't mean I don't see it. It's actually right here on my monitor, right here. So if I have this earpiece so I can hear, and I also can see. So just be aware that if you want to come join the fun, join the fun. Let's have ourselves a blast over here. And other than that, if you're wanting access to the notes for today's lecture, they'll be available on Patreon and Subscribestar later today. So, and that also comes with all sorts of other perks. This will be available at the supporter access tier and above. So I just had to mention that because sometimes people ask me, Dan, how do I get your notes? It's available at the supporter access tier or above. It's absolutely affordable. It's rates that you cannot compete with when it comes to bigger schools, okay? So just need to point that out, is that like if you're, say, taking classes right now and you're looking at a way to boost your learning on these topics, please, I encourage you, join up, have the fun with us, come get access to the learning materials, join the Discord server. We have ourselves a blast, and join the fun. Computer science is something anybody can do if they really put the heart into it and they really want to strive and succeed at learning it. But I agree, it's not for everybody. But the thing is, it most certainly is for everybody that is interested in it and wants to pursue it. I think that, and that's generally one of my missions here, is to get you excited about computer science. So, anyways, I'm just going to check a couple quick things before we get going. So I forgot to turn off the ringer on the phone down here, down here at the studio. But anyways, we're going to be talking today about some. So I'll recap you on things in a moment, but the main topic for today's lecture is something called Epsilon-Nondeterministic Finite Automaton, which is abbreviated as an Epsilon NFA. So we're going to be talking about these today, and we'll talk about why, like what is it all about? Like, why would one desire the features of such an NFA? We're also going to talk about how this relates to DFAs. So previously we had talked all about this relationship that NFAs and DFAs have. And what we're going to do today is we're going to see what we could do with our NFA if we add a few more features. Because in the same spirit as our previous lessons, we were seeing, hey, look, can we take our NFA and give it, like, can we give a DFA, add more features to it, and can it still recognize only regular languages? So in some essence, it's like, okay, well, if it only recognizes regular languages, like, first, I don't know if there's other languages. We haven't talked about that. The other thing is that, okay, so it gives us a richer set of design tools that we can use for designing our finite automata. So just keep that in mind. It's not just, oh, it's not supposed to be just a Debbie Downer. Be like, hey, look, it's not just that, oh yeah, it's only recognizes regular languages, so there's something about that that's a limitation, most certainly. But at the same time, by exploring more of these finite state machines and their feature sets, we'll see if we can come up with ways to make it easier for us to recognize certain languages for finite automaton. Okay, so let's get into things here today. So just as a quick reminder, if you hear any loud barking noises, don't worry. It's just a little puppy. She's just in her playpen, okay? Don't worry about it. She's in good hands. She's just very, very excited, and she needs to be in her playpen for now, because she's just a little puppy, and she's learning how to go potty. So, anyways, let's get into things today. Okay. So previously we had talked about non-deterministic finite automata, and we talked about a few big deal things. First, we talked about non-determinism. In addition, we also talked about this broader idea that if I give you a non-deterministic finite automaton, NFA, it recognizes some language just like a DFA would. So a natural question is, okay, so what languages are NFA capable of recognizing? Well, last time we established that for any NFA, which, by the way, if it's some NFA called N, its language of that NFA, and suppose I have a DFA, say, as a language D. Those are all the strings for which it accepts. That if I give you any NFA, I can show you how to construct a DFA such that L of D is equal to L of N, and I can also do the same thing in the other direction, meaning that NFAs and DFAs are computationally equivalent. There's an equivalency between the languages that these machines recognize. So that leads me to some natural questions. So first thing, can I add more features in the same spirit as a previous question I had asked some time ago? Can I add more features to the NFA such that, say, and on two sides. One, you can imagine I give you the NFA, and I want to add some more features so that it doesn't have this relationship. That's one possibility. Another possibility is that I could try to add features to this NFA such that this relationship is generally still preserved. But it makes it easier for us to design a finite state machine or finite automaton such that it recognizes some language. So we're going to be doing the latter here today. And my goal will be to convince you that with these new features for this variant of an NFA, that it still will have a corresponding DFA. So the variant of an NFA we're going to talk about here is what was called an Epsilon NFA. Or in other words, a non-deterministic finite automaton with Epsilon-Transitions. So that brings me to what I want to talk about here. So what feature are we going to be adding here? So this is one possibility of something we could try adding to the NFA. So consider an extension of NFAs where we permit transitions on epsilon. And remember, epsilon is the empty string. So you might ask, what does that even mean? Like what does it mean where it can transition on the empty string? So let me put it in other words for us. Since epsilon consists of no symbols, so the empty string indeed has no symbols, transitions can be made spontaneously. So you got to think back to how these machines operate. So I'm going to keep this at a high level for now. Is you imagine it takes in the string, right? It has a string that it takes in. Say it's string W, and W say is like 0, 1, 1, 1, 0, 0, or something like that. So what it does is it reads one symbol at a time, right? That's what the machine we're used to does. It reads one symbol at a time, it consumes one of the symbols, and it proceeds to the next one. And it finishes execution once it finishes reading or consuming all the symbols of the string, right? So what does this mean in this context then? Well, it means that you can transition without needing to consume a symbol. So meaning, for example, suppose that you transitioned on one of these symbols and you say we're going to read this 1 next. What we're going to allow to have happen is it's allowed to transition without consuming that symbol 1. But it will eventually have to read the 1. It's just that we're allowed to transition on no symbols. That's what this is all about. So in some sense, it's like if you had, say, a pet dog, a little puppy dog, and the puppy dog does something for you, and you give the puppy dog a treat. You could still give the puppy dog a treat regardless, right? So perhaps we would like to have it so that the dog doesn't have to do something to get the treat. We just want to give the treat. So this provides some new design features. And I must emphasize these are design features. So this provides some design features. So I thought I'll give you a couple of examples of so-called epsilon NFA, which we're going to define after we see the two examples. But I think once you get a high-level idea of what this extension does, the definition will flow quite naturally. So let's consider something that we've actually seen how we could do with an NFA, but we can make it actually much easier to do. Let's consider recognizing keywords. So let's revisit the idea of recognizing keywords. So it's a little easier to design with an Epsilon NFA a machine that recognizes keywords in a much more broader way. Now, there are ways naturally to do it, as we've seen with just an NFA. But let me give you an example of what I'm talking about. So suppose that the alphabet, suppose that we're going to consider strings over the lowercase alphabetical letters of the English language. So suppose that we have this alphabet that all of our strings are going to be over. And suppose that I wanted to detect certain key phrases, just like we've talked about before. So I want to detect, let's try to make it so that we can detect two words. Let's try to detect Pam or no. Let's see if we can come up with an Epsilon NFA that uses this feature. So if we did this with an NFA, it's not very terribly difficult to do this. But the issue at hand is that I would like it to be so it's even easier to do and perform or construct such a machine. So let's do this. So we're going to start off with a start state. I'm just going to numerically label these states, which is a little different than when I usually do this. So sometimes I always like to show you little bits of pieces of things that maybe we haven't seen before. But some people, when there's many transitions that are going to occur, such as over some set, you might want to label, you can also label these over said set. So that just simply means all of the symbols in this set. So this would be A, comma B, comma C, comma all the way up to Z. So on any one of the input symbols here, it's going to transition on to 0 here. However, I would like it so that it can detect Pam or no. So if we were doing this with an NFA, you would have it where you can transition on the P, and you would have it on possibly one goes on the N. However, one thing we have to be careful about when we're doing this is if we have many key phrases, we have to be careful what exactly we would desire. Now, Epsilon NFAs make this much easier to do. Now, you can, of course, do it with an NFA. It's not too terribly challenging, but it gives you a much more general framework for how you might go about this. So check this out. So we're going to use the same strategy we would be using to detect if the string consists of some key phrase that we're used to from a DFA. So that's the first thing you should notice here. Suppose I have Pam here. I just have a path that reads Pam. Anytime it does not say P on this one, it's just like the thread dying, gets killed, like we talked about with NFA, right? So you can imagine I compose two smaller NFAs, and then I can bring them together. And what I can do is I can use an epsilon transition to get me over here for free. So what do I mean by this? Well, what I'm saying is, if say for example, you're reading in the string, you don't have to actually read a symbol to get to state 1. So you're going to see that this actually has a natural mechanism, which is referred to as an epsilon closure, which I'm going to define when we talk about the formal definition of computing for an epsilon NFA. It essentially allows us to be in state 0 and state 1 freely, right? Like, because I can just go here for free, right? I don't have to consume the symbol. I don't have to read the symbol directly. I just read the empty string. So it means that I can be over here, allowing a thread or continual guesses to produce here, but I could freely go to state 1 at any time from here. So for example, the minute I see a P, I can be in state 1 and I can read Pam, if Pam was indeed the sequence that came. But this also is a nice pattern because now I can add more states and use the same strategy. So say if I want to have it now, or I want to read no, right? Well, what can I do? Well, I don't have to add anything special here except for an epsilon transition. But there's something I haven't quite done. Remember, as soon as I detect Pam, I'm going to... So I'm going to have it where I just see those strings. But do you notice here that... So I would like to be able to detect if these strings are present. But the thing is, I'm just putting in the context for which if you're typing in a sequence here, if I wanted to allow there to be more symbols, I would design this NFA a little bit differently. But do you see how I can use these epsilon transitions just to have it where if I want to have more keywords, it's just an epsilon transition and a pathway like this. So specifically so just to be a little bit clear about what I mean by detecting Pam or no, this would be, for example, if you have a sequence of keystrokes. So imagine you have the most recent string is typed in on your keyboard. I would like to know if it's Pam or no. So this is the scenario. So let me be a little bit more specific, because otherwise you would have to add more. You would have to add a little bit more here, right? Because there might be more strings. Sorry, not strings, symbols. More symbols. So when I say detect, what I'm saying is if the most recently typed string of symbols is Pam or no. Notice I'm using an or here. There's actually a really nice pattern or structure that the epsilon NFA gives you, is if you have a property like an or, the epsilon transitions give you options for choosing one of the pathways. In fact, you could choose on all of them because it's an NFA, right? So you just imagine you're giving a bunch of keystrokes and it remembers the most recently typed string. You pump it through here and you check if it has Pam or no. So this would be, so another way of putting this is that, does it end with Pam or no? So in this example here, for instance, what this one would do is it would detect if Pam or no is the most recently typed string of symbols. Say if you're typing in this on a keyboard. Or in other words, the string ends with Pam or no. Exactly, Miss Kitty. Exactly. So this is an example of one application. Let's consider another one. So you can actually use the epsilon NFA to simplify the design process for detecting key phrases. And you can pick up all of the stuff that you're familiar with from NFAs to augment, say, for example, this epsilon NFA. So, for example, if you wanted to have it, where it just contains Pam or no, you can easily pick up the strategies that we've seen before. However, here it's just simply if Pam or no is at the end of the string, because we're looking at what's most recently typed. Let's consider another example. So we might want to consider, and this is a nice classic example, is say you want to have a machine that's for reading decimals. Right? There's many machines that you want to read decimals on. Like say you can even think of something like a calculator, right? Suppose I want to read some decimals. So I'm going to give you an epsilon NFA that's going to be capable of doing the following. So I'm going to give you some specifications. Below is a epsilon NFA. What's an epsilon NFA? That accepts decimal numbers. with the following format. The following format. So what we're going to have is the string is always going to have a particular form to it. The first thing is it's going to have an optional plus or minus sign. So it can be positive or negative. It may have a string of digits. Then I'll have a decimal point, potentially, right? And it may have another string of digits, right? Another string of digits. Note that that if we want to have it where we want to have it, where it's a string of digits and another string of digits, this decimal point has to be present, right? But note that we just don't put a decimal, right? We have to have at least one. We have to at least. Let me just make a note about this. Note that it must be that one of 2 or 4. So this string of digits or this other string of digits must contain at least one digit. I.e., the string must be non-empty. That's another way of me putting this. So the string must be non-empty. That's a really funny word right there. It looks like the string sort of melted into itself, like cheese. So we're going to design an epsilon NFA that has all of these features. So it's able to accept any decimal number written out as a string in the following form. So let's try drawing this out. So let's try to come up with something that follows these rules. So we're going to have Q0. It's going to be our start state. Now, as an optional plus or minus sign, so the minute you hear optional, you might suggest to use an epsilon transition, right? Because it's just like if I have the puppy dog, I can give the puppy dog a treat, or the puppy dog might want to do a trick, and it gets the treat. So if you're leeway like that, this sounds like an option, right? So let's do that. So let's have it where it has an epsilon transition. It can read a plus or a minus, but only one of these, right? And then it takes us to a state we're going to call Q1. Now, once it's at this stage, it's supposed to take in a string of digits. So that means it could be a 0, could be a 1, could be a 2, could be all the way up to 9, right? So just keep in mind that the reason why we're including 0 in here is it's just padding on everything, right? It's just like if you had a whole bunch of zeros sitting out in front. But if you don't like that, we can... Actually, we'll keep it like this. But if you don't like this epsilon NFA, I encourage you to think about how you would have it such that you forbid this in the design. Notice here I don't have anything that says that we're not allowed to have a 0 sitting out front like this. So we have a decimal point. So upon having a decimal point, it has to be that if you get a decimal point, there has to be another string of numbers that come after it, right? Because in this case, it could be the case that you just go right to the decimal point, right? But that means that there's going to be at least one digit. So we're going to have 0, 1, all the way up to 9. Any one of these symbols would suffice. And then on Q3, we can read in some more symbols. However, another possibility is as follows. It could be the case, because remember, notice it says, note that it must be that one of 2 or 4 must contain at least 1 digit. So in this case, notice that it doesn't require there to be a digit before, right? But it requires it after the decimal. I want to make sure that there's a case for which we guarantee that there is at least 1 digit before the decimal point. Then we transition on the decimal. And now, upon reading any more, we'll have it on epsilon transition. And finally, let it accept. But notice that I'm using the epsilon transition here to optionally allow me to get to the final or accepting state. I'm not using it in a way that's just like, it's just now it's an option to say, do you want to stop? So this is actually another helpful feature of having the epsilon transition, is if I'm reading in more stuff, the epsilon transition allows me to freely go over to the accepting state without having to read a symbol. Very nice, right? So this gives you a couple different ways you might use the epsilon transitions. In the first case, we want to recognize some keywords. The epsilon transitions make it easier to design it such that you have certain target strings. That maybe, for example, what we had was you look for it as the most recently typed sequence or the end of the string. Versus here, we might use it to represent options, such as in the case for which I want to put something at the beginning of the string. Or I may want to have it where I allow it to freely go to the accepting state if, say, there's nothing else. So if I have nothing else to read, I can allow it to just freely go to the accepting state, because once it gets over here, it can read any symbols you want, and it's good enough. So that brings me to defining what an epsilon NFA is. So hopefully you understand the main idea here. So the feature is that we allow it to transition even when it doesn't read a symbol. So it gives us effectively what amounts to an option. Which you can use in many different ways. So let's consider now the definition of a non-deterministic finite automaton. A non-deterministic finite automaton with epsilon transitions. So this is abbreviated as an epsilon NFA. And I'll usually refer to it in that sense, but this is the full name. And yes, that is terribly straight. So let's proceed. So I'm going to keep the definition as brief as I can about this, at least for our presentation here. I'm going to presume you know what an NFA is, because the definition is nearly identical with one major difference. A epsilon NFA E is a 5-tuple. Q sigma, which is so this is our set of states, the input symbols. Delta is the transition function. Q0 is the start state, and F is the set of final states, where everything is as in NFA, except we allow the transition function to behave a little differently. So here's how we're going to formally define this, and I'll explain it in plain words here. So it's going to look not that much different. So delta is going to be defined as follows. So it takes in a state and an input symbol, or, so this is together here, so, or epsilon. So now I've introduced epsilon into into what can be the string here for the second input for the transition function. Please note that epsilon is not a part of the input symbols. It is not. And it outputs a subset of the states. So some member of the power set of the states. So any subset of them. So it gives you a subset of the set of states. So in plain language, so this is a state. So given a state, given an input symbol, or epsilon, it gives you a subset of the states. So this part right here is the only part that differs. So please remember, so I'm going to make a remark about this. Epsilon does not belong to the set of input symbols. Yes, Miss Kitty, I haven't forgotten. That's why we're writing this. The set of input symbols, sigma, it is a feature of the NFA, of the epsilon NFA. So notice there's nothing too terribly surprising about this definition. It allows it so that the transition function can now transition on epsilon, meaning it doesn't have to consume a symbol. That's an epsilon NFA. Are there any questions so far? Any questions? Any questions? Miss Kitty, you have any questions? Any questions? Do you have any questions, Miss Kitty? You don't? You don't? That's awfully nice of you. As long as you behave yourself, okay? Yes, yes, yes. But Daniel's gonna have to, sorry, I'm just talking to Miss Kitty here. Daniel's gonna have to clean the boards. So if you have any questions, put them in the chat. I'm gonna erase the boards here. Miss Kitty, you need to calm down. Going a little crazy here. So we've defined what an epsilon NFA is. But we sort of have this high-level view of what it is, how it computes. So I'm going to be talking about that next. Miss Kitty, that's just a dot on the board. Why are you staring at that? That's so weird. I guess you really are you're really a big attention hog there. What are you doing? Yes, you're funny. Yes, you're funny. You're funny cat. Yeah. Just going to drink a little water here. Okay, Miss Kitty, you're going to have to behave yourself, okay? Just going to make sure I know where we're going here. Yes, Miss Kitty. Yeah, I know you're very funny. You're very funny. I know. But it's time to go down, okay? Okay, Miss Kitty? It's time to go down. Time to go down. She's holding my notes ransom. I have a spray bottle. Okay, there we go. There we go. We're free of Miss Kitty. For now. I'm not sure she'll be back. So, anyways, next what we're going to be doing is we're going to be now exploring how an epsilon NFA actually works. So how how does an epsilon NFA work? So in plain language, I'm just asking how it works. So you naturally will know if we see what an NFA and a DFA does in a more exact way. It means we're going to have to define an extended transition function that tells us how computations on the machine are carried out. But to do that, to answer this question, I'm going to introduce a concept called an epsilon closure. So to answer this, we use the concept of a epsilon closure of a state. So we're going to define this concept of an epsilon closure of a state. So what this is going to represent is how we allow the transitions to freely occur without consuming or reading a symbol. So epsilon closures are going to capture this behavior. So I'm going to denote this. I'm going to call this eClose Q. So if I give you, so this is a state, I give it to you, it gives me back a set of states. So informally, so I'm going to define it formally, but informally, eClose of Q, so for state Q, returns all states that can be transitioned to by epsilon, the empty string, via state Q. So like I said, we give that option. The epsilon NFA will use an epsilon closure to get to those states freely. So that's the intuition behind this. So let me define this a little bit more carefully. So once I define it more carefully, we'll see some examples. So epsilon closure. So define eClose Q inductively as follows. So we're going to define it inductively. So we're going to have a base case, and then we'll have an inductive part. So the basis of the definition is that state Q must be in eClose of Q. So anytime I give you a state Q, it has to be by definition that eClose of Q contains Q. You might say, why? So these are states that can be transitioned to by epsilon. And we already know that if you just don't consume a symbol, for free, you end up in the exact same state, right? So this makes a lot of sense, right? So the inductive part is if P, so if a state P is in eClose Q, then so are all states in delta P epsilon. So it means that when you transition on epsilon, any of the states that you get as a result of that also have to be in eClose. So one other detail I want to add, it just as a note. So we can also define eClose on a set of states too. Given a set S of states, eClose of S is just simply going to be the union of all. So I'm going to take all of the resulting epsilon closures on the states within this set. So we're going to do some examples seeing how epsilon closures work. One remark I do need to make is that if you give me an empty set and you apply epsilon closure on that, it still is an empty set. Just keep that in mind. So let's do an example. So let's try applying this definition. So we're going to try applying epsilon closures on various states of this epsilon NFA, just to see what happens. So 1, 2, 3, 4. We're going to have 6 states, where 5 is going to be the final state. So I'm going to have an epsilon transition from 0 to 1. I'm going to have an epsilon transition from 0 to 2. I'm going to have an epsilon transition from 1 to 3. I'm going to have an epsilon let's make it an A. Make it so it reads an A. It goes from 2 to 4. Let's make it so it reads a B. You go from 3 to 4. But we'll make the rest here epsilon transitions. So from 3 to 5 and from 4 to 5, those are epsilon transitions. But I'm going to allow it to keep reading B's once it's in state 5. so let's see what happens. So what we're going to do is we're going to see what epsilon closure does if I give it a state. And then we'll see what happens if I give it a set of states. Just so we can see some examples of how this works. So let's consider the epsilon closure of state 0. So what would this be then? So first, we know that the state itself is a part of this set, right? So we know for certain state 0 has to be in this set. That's what the basis of the definition says. Now, this is where it gets a little tricky at first, because you also have to think about this carefully, because this definition is inductive. Or in other words, you can think of it as recursive if you think about it like a process that keeps occurring until this definition is satisfied. So if there's a state that's going to be an E-close of Q, then so are all states in this, right? That's what it says. But what does that mean then? What does that mean then? So it says if that's an E-close of Q, then so are all the states in this. But what does that mean? That means that if I apply an epsilon closure on a state, I end up with potentially more states. And those states also, if they are a part of this, then so are those ones on transitions with epsilon. So you're going to see quite quickly that every time you do this, you can see that it's essentially a process where I'm just going to keep accumulating all of those epsilon transitions from each state I discover. So just as an example, if you were to just literally just interpret if P is in this, so if 0, so now I want to walk through what this means. So if you imagine you're given a state of the epsilon NFA. So if it's saying if 0 is an epsilon closure Q, then so are all the states that you could transition to. So if 0 is in there, then all the ones that you could transition to on 0 using epsilon also are as well. So watch this. So that means that 1 is, and so is 2. Because notice there's epsilon transitions that get you to these states. But now, notice that I have states 1 and 2 in the set. So if 1 is an epsilon closure, because remember, it's a conditional statement. So if 1 is in E-close of this state, then so are all of its states that you could transition to on epsilon. So notice that 1 could transition to 3 on epsilon, so 3 is also in here. Now, 2. Notice that there's no epsilon transitions here. You just end up with 2, right? So, we're done with 2. How about 3? So if 3 is an epsilon closure Q, which it is presently, then so are all the other states that you could transition on that state with Q. And sorry, with P. which P is 3 here. So I have epsilon, so I can go to 5, right? But notice I can't go to 4. Notice 5 doesn't have any transitions that head outward to a different state. So you know that this is actually the epsilon closure of 0. So you keep repeatedly applying the inductive definition here. So every time you discover another state, if that is indeed a part of this set of states, then so are all of the so all the states you could reach via an epsilon transition. And you keep repeatedly applying this process. Let's do another example. Let's consider epsilon closure on state 1. So if I look at state 1, okay, 1 by definition is in the epsilon closure of 1. But notice there's an epsilon transition, 3. Well, if 3 is a part of the epsilon closure of 1, then so are all the transitions on state 3 given epsilon. So notice that I can go to 5, right? But I can't go to 4. So that's the epsilon closure of 1. Let's continue. Let's try the epsilon closure of state 2. So notice that 2 by definition is in the epsilon closure of 2. But notice there's no epsilon transitions. So if I just give you epsilon with that state, it's not going anywhere. So notice it's just 2. How about epsilon closure of 3? Okay, so now, akin to our previous example, 3 by definition is in the epsilon closure of 3, of state 3. There's epsilon transition to 5, but nothing to 4. Notice there's nothing outward that direction. So this is the epsilon closure of 3. How about the epsilon closure of 4? So state 4. So what would be the epsilon closure of state 4? What would it be? Well, notice that there's an epsilon transition from 4 to 5. So 4 by definition is in the epsilon closure of 4. Notice there's an epsilon transition on 4 to get me to 5. Nothing leaves 5. So that's the epsilon closure of 4. How about epsilon closure of 5? Well, 5, there's nothing outgoing from 5, but by definition, 5 is in the epsilon closure of 5. So now we've examined all of the states. Let's do an example where I give you a set of states. So suppose I defined the epsilon closure with a set of states. Suppose I give you states 2 and 5. Well, this is actually equal to the epsilon closure of 2 union the epsilon closure of 5, right? That's what we defined the epsilon closure of a set of states is. So E close of 2 is just 2, right? So this is just 2, the set containing state 2. And how about 5? How about 5? Well, it's just 5, right? Just the set containing state 5. So if I take the union of the result, I end up with just the set containing states 2 and 5. And that's it. So that's how epsilon closures work. So now that we have this mechanism that models these so-called epsilon transitions that we've talked about, let's now define the extended transition function using epsilon closures. So once we have this, we have a way of defining the computations of an epsilon NFA. And you're going to see very quickly that this is not going to be very much different than what we had with the NFA. It's just, we're going to add this mechanism into here. So the extended transition function for epsilon NFAs is next. So let's define this together. So just like what we had for extended transition functions before, this will be defined on a string, not just a symbol, or the empty string in our case as well. So the extended transition function and I'll use similar notation as before. Function delta hat is defined as follows. So there's nothing going to be really surprising about this example here. It's just going to be that we're going to have it where we're going to incorporate these epsilon closures. And I want you to really identify those parts that are different, because it'll give you an intuition for the relationship it has with an NFA and perhaps a DFA. So we're going to have the basis. So the basis is just simply that delta hat. So if I give you epsilon on a given state, well, what would we need to incorporate here? Well, if it was just an NFA, right? This would just be the set of states that just contains Q, right? It's just a set with the Q in it, right? That's what would happen with an NFA, a vanilla NFA. What would be different here for the epsilon NFA? Well, it's allowed to transition on those epsilon transitions, right? It doesn't have to read a symbol. So that means it can be on an epsilon closure of that state. How about the induction or inductive part? Just waiting for the phone to stop ringing. Don't want you to be disrupted by the phone. Okay, so let's get back to this. So the inductive part of our definition for delta hat is as follows. So first I should probably describe it first informally, and then I'll describe it formally. But there shouldn't be anything too terribly surprising here. Less formally, after computing the set of states as in an NFA, epsilon closure is applied. Epsilon closure is applied to all the resulting states. So let me describe this more formally now. Suppose, so the string W is of the form W is equal to XA, where A is the last symbol of W, and X is everything but A. Where A is the last symbol of W. And akin to what we talked about with an NFA, we're going to let delta hat, given a state, to start off with Q, where I read off X. Suppose it gives me a set of states, P1, P2, all the way up to PK. Then it has to be the delta hat QW So delta hat on state Q, when I read W, what would it be? What would it be? Well, what did it look like for an NFA? So remember, we compute the set of states like we would for an NFA first. Then what we do? We apply an epsilon closure. So how did we do that for the NFA? Well, over each one of these states, so each one of these, P1 all the way to PK, you'd apply the transition function. All the resulting sets of states all get lumped together via union, and that's the resulting set of states for an NFA. However, now the wrinkle is that, yeah, we could transition for free on the epsilons, on epsilon, right? So that's quite naturally going to get modeled into this. So let me just write out the part for the NFA part. So for each one of the states, I transition on A, give me a set of states. And then what happens is I apply the epsilon closure to the resulting set. So now that we have the extended transition function, this tells us exactly how it's going to compute strings for the epsilon NFA. I can now define what the language of an epsilon NFA is. So now that we have this, what I want you to do is go back to those previous examples that we had for epsilon NFAs. And I would like you to try out some strings using this definition akin to what we did with the NFA. So give that a try. But I want to define one last thing for us, is the language of an epsilon NFA. So let's define what the language of an epsilon NFA is then. It's not going to be very terribly surprising, akin to what we talked about with an NFA. So given epsilon NFA E, which is going to be equal to, actually I'll write E over here, NFA E. So if I give you a set of states, set of input symbols, delta Q0F, then the language of the epsilon NFAE is the set of strings, language, such that delta hat Q0W, how did we define it for an NFA? Well, it was this. We wanted to make sure that there's at least one state in here, in the set of states, that is one of the final states, right? So we take it and intersect it with F, meaning that now if this is a non-empty set, the result means that there's at least one element in common among the two, meaning that there's at least one state in F that belongs into this set as well. As long as that's not empty. But yeah, this is the language of an epsilon NFA. And now that you have this, now you can talk about claims all about how you recognize some language. You can pick up all the tools that we've discussed previously for NFAs and DFAs and formalize it a little further. Say, for example, you want to pick up this and prove the correctness of the epsilon NFA. You can use some of the techniques we've seen before using this definition of the language of that epsilon NFA. Pretty nifty, right? So, are there any questions? Any questions? Any questions? So what we're going to be doing next is we're going to actually be considering the question. The fundamental question from the beginning of today's lecture is, if I give you an epsilon NFA, is there a DFA? If I buff up the NFA to have these new features, does it still have a corresponding DFA? And the answer is yes, it does. It does. So if you wanted to design your NFA with it so it has epsilon transitions, you most certainly can. You can still get a resulting DFA. The version of the subset construction that we're going to employ is still going to be the lazy counterpart, but I must stress that this specific one is often associated with the computer scientists that discovered this subset construction. So the name is escaping me at the moment. It should be Dana Scott and Rabin. Yeah, I think it's Scott and Rabin, if I remember me correctly. It's been quite a while since I've read up in some of the history around this, but either way, it was granted a prestigious award just for this construction. It's a big deal. It's a big deal. Before we actually get into that, I thought I would talk a little bit about that. So you might ask, Dan, why does all this matter? In quotation marks. First, it is a fundamental question about computation. So yeah, it does matter just on those merits alone, because it's a statement about abstract machines and their equivalencies. But also, it's a fundamental question about if you design one of these machines. Because keep in mind, an epsilon NFA, an FA, these all have combinatorial descriptions, meaning that you can describe them as sets. You can indeed use their extended transition functions to compute the set of states. You would simulate this on a computer, for example. It might be a little expensive, depending on how big big your machine is. For DFA, it's rather straightforward, but for those other ones, you would be simulating this process. But the point I'm getting at is that when you have and come up with an epsilon NFA or an NFA, the idea is that if we can convert this over to a DFA, or say if you just want an NFA, there exists ways to do this. So there's going to be other characterizations of regular languages, such as regular expressions. And if ever I wanted to move from one characterization of the regular languages to another, I can use these constructions to get myself over there. So this by no means is this the only type of construction we will see. We'll actually see some more examples where, for instance, I'm getting really excited here. For instance, we're going to see how we can take, and we won't see this today, but we'll be seeing it in probably in a couple weeks. We'll see how we could take a regular expression and convert it over to an abstract machine. So if you give me a regular expression, I can show you how to construct an epsilon NFA. And what I'm going to be showing you here today, for example, is I'm going to be showing you how to take an epsilon NFA and turn it into a DFA. So there's going to be a very fascinating relationship that all these different characterizations have. Some refer to this as Kleini's theorem. I'll usually refer to it in this way. So just to give you a little bit of hindsight of where we're going in the next upcoming weeks, is I'll be showing you, if I give you like a DFA, and I give you an epsilon NFA and a regular expression, that there's a way to go between all of these. So what'll happen is that there's actually ways to go between any of these manifestations. And each one has their own place in the land of computation. So you might heard of things called regular expressions. These are very often used for detecting complicated formats of strings. So for example, if you want to come up with a string that detects a key phrase, regular expressions give you a natural way of describing them in a semantic way. As opposed to how we do with DFAs, we might design a machine that does something like this, but it's not expressible in a nice, simple, linear way, which is what a regular expression is rather nice for. So naturally, whenever you have one of these and you're like, hey, look, I want to actually implement, I want it to carry out the regular expression. How can I do that? We just convert it over to one of these other types of abstract machines. You can include NFAs in here too. And you could simulate that NFA, or you can, for example, just literally carry it out, right? So any one of these is a manifestation of the regular expression. So this stuff is used all the time in compiler theory. And if you want to do parsing of large, more complicated strings, also in addition to this, if you were interested in lexicographical analysis, you might use some of the things that we talk about here. Some of the bedrock of the theory underneath a lot of that technology comes from a lot of the things we're talking about here. So please don't look at this and say, oh, well, Dan, it's theory of computation. It has to be this really abstract thing that has nothing to do with the real world. It has everything to do with computing these days. So I don't really agree with that assessment. That's basically what I'm trying to get at, is there's numerous applications for the things we're talking about here. I don't talk about them so much here. Maybe I will if people are interested in that. But the point is that we're trying to understand what computation is and aspects of it. So what does it mean to have a computer, for example? At first it sounds like a really oh, it's like my laptop, right? It's like my laptop. But the thing is, sorry, I had to stop Miss Kitty there. Miss Kitty was getting really excited. So if you're in a situation like, okay, so what is a computer? Well, what is it capable of? What limitations does it have? These are not questions you can answer with just one computer program. Like these are much more universal types of questions, namely what isn't possible. And this is what a lot of the theory we're talking about is fundamentally about. Right now we're looking at what's possible, and naturally there's going to be a complement to what we are talking about here, what isn't possible. So that's the computability aspect of this discussion, which you cannot just simply say, oh, I have some cool application. Isn't that cool? Cool. Like, that's how some people sell a lot of these ideas. That's the difference between being a merchant of ideas versus actually understanding computer science. That's really what I'm trying to tell you about here. So we're trying to get to the heart of the computer science that we're discussing here. I'm not here to just dangle keys in front of you like some salesman would. So let's now talk about how we can construct take an epsilon NFA and construct a corresponding DFA. So let's get into this. Okie doke. So before we get into this, I'm just going to give you a heads up. We're going to go a little slower for this example, and then I'll do another example I go a little faster. So hopefully that's okay with everybody. Just because I had to be a little careful because we've talked only recently about epsilon closure, so it's a good idea I kind of go through this carefully. So I'm just gonna take a look carefully, make sure we're on the right pace here. Okay. So I'm just moving this on over here. So previously we talked about what an epsilon NFA is. We talked also about how it computes on an input string. Now I want to address a fundamental question now. Is if I give you an epsilon NFA, is there a corresponding deterministic finite automaton, or DFA, that recognizes the same language? And the answer is yes. Yes, there is. And what we can do is we could actually take what we discussed previously about the subset construction and incorporate the aspects of the definition of the epsilon NFA into it. So we're going to talk about how we can take an epsilon NFA and get a resulting DFA that recognizes the same language. So we'll talk about epsilon NFA to DFA conversion. So we're going to be taking the version of the subset construction we had, namely the lazy counterpart we discussed previously, and we're going to be adapting it with the definition of how an epsilon NFA computes. So if you notice this, it's a piece of cake. So if you understood the subset construction, this modified version, which is much more general, by the way, because every NFA is an epsilon NFA, it just doesn't have any epsilon transitions, right? This is a much more generalized way of me talking about this. So naturally, we can also employ a modified version of the, and I'm going to presume it's the lazy counterpart, but you can easily see it in another circumstance. So I'll define it first in the way that we talked about previously. Modified version of the lazy subset construction to build a DFA D, which is going to be equal to QD sigma. Its input symbols are going to be the exact same. Delta D QD FD. So the subscripts I'm just using to denote those associated with the DFA. From an epsilon NFA, E, which is going to have states QE, sigma, delta E, Q0, FE. So just like I did for the subset construction in the lazy counterpart, I'm going to first talk about what we're going to have each aspect of this DFA be. So we're going to talk about what the states are. We're going to talk about what the transition function is going to look like. We're also going to talk about any other little wrinkles, like even the start state. The start state might differ, right? So let's first talk about the states. So the states. So it's going to be a set of subsets S, which are going to be a subset of QE, where each S is going to be the epsilon closure of S. So the technical term, by the way, for this is that this is often referred to as the epsilon closed subset of QE. That's what this is referred to as. Note that if it was empty, then the empty set is also an epsilon closed set as well. So essentially I'm just saying, hey, look, so for each one of the subsets, you'd imagine you have the epsilon closed version of it. So QD, so this is the set of states for the DFA, can be constructed by beginning with the start state QD, which I'm going to define this below. So I haven't defined what QD is quite yet. So you start at QD, and until no new states are discovered, akin to the lazy subset construction, are discovered as a result of following transitions. Add any new states to QD found as a result of combining the lazy subset construction. We previously discussed this for NFAs with the transition computation below. So I'll give you that in a moment. But this shouldn't be terribly surprising. So it'll look a lot like the lazy subset construction we had before. Just with just a couple wrinkles. So next we're going to need to know what the start state is going to be. So any suggestions of what the start state should be? What's the start state? Let's think about it. What would be the start state? Well, think about it. If you had Q0, which is the start state of the of the epsilon NFA, what would it be? So what subset, which remember in the lazy subset construction, this would be a label that represents a state in the DFA. What would it look like? Would it just be Q0, like in a set? No, it won't necessarily be that. It'll have to be all of the states as a result of the epsilon closure on that start state. So QD, so this is what I was referring to as being defined below. So it's going to be the epsilon closure of Q0. So whatever that subset will be, whatever that is the start state. So this, whatever this is going to be the label for that start state for the DFA. Final states. Let's talk about the final states. So FD is going to be defined formally as follows. So let me just write it out first, and then I'll pin it down a little further. So it's going to be some set S, such that S is in QE and the intersection of these two things, these two sets. Actually, I was just thinking to myself, technically speaking, S is a subset. I'm pretty sure it's, when I say is n, I should say is contained. Is in is, I'm referring to it in terms of a subset. S intersect FE is not equal to the empty set. That is, so it sounds a little bit weird at first, so let's just let's parse this. That is, the sets of final states, which remember, these are labels. They're states in the DFA. Is of a final, sorry, it's the set of not final states, the set of states that contain at least one accepting state. Of E. So all of those subsets, they're final states, which is not terribly surprising because it should remind you of the subset construction, as per usual. So now we got to talk about transitions. And this is really kind of the big wrinkle other than what we talked about just above for the start state. And just generally how this works, where we're going to have it where wherever the set of states would be, they're going to be resulted versions for which we apply epsilon closures. This is where this mechanism is going to play out, as I discussed previously. So for transitions, we're going to let set S be P1, P2, all the way up to Pk. And we're going to define delta D for, remember, this is going to represent a label, but it is a subset when we think about it in terms of the context of the epsilon NFA. So S and A is computed as follows. So this should first remind you of the subset construction, just vanilla with an NFA. So 1, you're going to compute just as per usual each of these transitions on the symbol A. You get these, lump them all together, and they'll end up with some set of states, right? It's some subset. So let the result be, I'm going to call them R1, R2, all the way up to some state Rm. So that's the first step. That shouldn't be very surprising. This is just what you would do in the subset construction, correct? As per usual with an NFA. But now we have to add in the part that makes this unique to an epsilon NFA that contains all NFAs, but this second step isn't terribly interesting for just an NFA. Okay, delta D S A is going to be equal to the epsilon closure, or E close on this set, the resulting set, as we've described previously when we talked about how an epsilon NFA computes, right? So this is actually how we can describe the DFA. So I think it's a good idea we see an example of us carrying out this lazy subset construction on an epsilon NFA to produce a DFA. So let's consider the following. So I thought it'd be a good idea we use the same example we did when we considered epsilon closures, seeing as we had some familiarity with how the epsilon closures worked for this particular epsilon NFA. So we're going to have 6 states. But we'll label it like this instead. I think I had it maybe the similar. If not, it's okay. There we go. So we're going to consider this epsilon NFA. This is going to be epsilon NFA E. And what we're going to do is we're going to produce a resulting DFA that's going to accept all strings that this epsilon FA accepts. Just for context, I thought it would be a good idea I show you just what the transition table for this would look like. Just because it makes it sometimes a little easier to spot anything that might be missing. So remember that because it's an epsilon NFA, it can transition on epsilon, which is, remember, it is not one of the input symbols. So we have 0, 1, 2, 3, 4, 5. And akin to what we talked about previously, each of these is just like an NFA. You're going to have a set of states in here. There's some subset of the states. So for example, there for epsilon, for when I read epsilon on 0, what state should it go to? 1 or 2, right? A, nothing. B, nothing, right? There's no transitions on A or B from the start state. 3, nothing, nothing. Right? Because on epsilon, it could go to 3. Okay, how about 2? Well, there's nothing for epsilon there. There's something for A, right? It can go to state 4. And B, nothing. Nothing. How about state 3? Well, on an epsilon move, we can go to 5, right? Nothing on A, but on B, we can go to state 4. For state 4, on epsilon, it could go to state 5, but nothing else, nothing else. But on state 5, it only could read more B's. There we go. So just for completeness, I gave you the transition table and the transition diagram for NFA-E here. So let's try applying the modified subset construction, or more broadly, a subset construction to this epsilon NFA. So what would be the start state of the resulting DFA? So for DFA-D, what's QD? So what did we say the start state is? It's the epsilon closure of the start state in the epsilon NFA, right? So the start state, so what would it be? So let's see. This is going to be the epsilon closure of Q0, which in this case, that's 0. But that's just simply 0, 1, 2, 3, and 5. I was about to put 4 in there, but yeah, it's no 4 in there. So this is the start state, is this subset, which is a label for that state. Now, we're going to go through this process of applying the lazy subset construction. So just to make this easier for us, I'm going to include a table here. And we're going to fill this in as we discover new states. So we know that the start state is going to be this one. That's what QD is. So now, let's think about this. How are we going to proceed now? So if I give you this subset, we have to use the transition function to figure out what's happening on each one of the input symbols. So if I apply it on A, what should it look like? Well, what would it be? Well, the definition, so remember there's two steps. First, we figure out all the set of states that you would transition to on A from each of these. Then you would apply the epsilon closure to that. So to figure out delta QD, so I want to figure out delta QD of A, but A in this case is just, it's literally A. It's not just a symbol. Actually, it is a symbol, sorry. It's not just a variable that represents a input symbol. It is quite literally A in this example. So what's that? Well, this is the union. So over all of these states, you apply this. So now we got to go through all of these and apply the transition function. The resulting ones let's see. 1a, two a, I'll get out of the way in a moment, 3a, 5a. So whatever the resulting label will get or subset will be the result of considering this. So what are we looking at for each one of these? So for state 0, so let's look at our table here. It might help us a little bit. That's empty, right, for 0 on A. 1 on A. 1 on A. That's nothing. 2 on A. 4. So far we got a set that contains 4. So that's 2 on A, right? So this one you have 4. All of these are empty so far. 3 on A. That's empty. How about 5 on A? That's empty. So the result of this is 4. Now, so that's the first step for what we're going to determine this cell of this transition table will have. What's the next step? We have to apply the epsilon closure on this. The epsilon closure of this state, because you go through each one of the states, you take and put them all together. So, the epsilon closure of state 4 is 4 and 5, right? And naturally, that's exactly what would go in this cell for the transition table. So, the same idea as we had before, except you're going to have this new step where you're just going to apply the epsilon closure. Otherwise, the process is the exact same. So let's see what else we got going on here. So just don't forget about that second part. So let's think about B then. So for all of these states, let's go through the same process now with B. So you just do all of these again, but now with B. Well, let's look at this. Okay, 0 with B. That's empty. 1 in B. Empty. 2 in B. Empty. 3 and B. 4, again. And 5 on B. We got 5. So now we have 4 and 5. That's what the result would be in this case, because I take the union of all the results there. Then I apply the epsilon closure on 4, the set containing 4 and 5, but that happens to also be the exact same set, 4, 5. So now that we've discovered a new state, namely this subset, we're going to add a row for it. And now let's do the same process. So next, we've got to consider all the transitions on A. So let's think about it. Let's try to do this a little bit faster this time. Say 4 on A. 4 on A. Okay. If I just consider 4, that's nothing there. 5 on A, nothing there. The epsilon closure of the empty set is still empty set. How about for B? Well, the transition for 4 on B. 4 on B, and nothing. On 5 on B, it stays in 5, right? But the epsilon closure of the set containing 5 is just the same set. this is technically a subset, hence we need to write a row for it. It's the one I next discovered. Well, this row is really easy, right? So it's just empty everywhere because notice there's no set of states, and for all of them, I'm just going to end up with another empty set. Taking on the epsilon closure of that set is still an empty set. That means now I got to consider this next discovered set of states. This one right here, I haven't accounted for that one yet. I'm just doing it in the order I discover them. So now I have 5. Okay, 5 on A. There's no transitions on 5 with an A. So you know right away that the epsilon closure is definitely not going to introduce anything else, because there's no epsilon transitions out of 5. And it's not transitioning on A at all, right? So if you're not convinced by this, just go through the same set of calculations that I did over here. Okay. Now we got B here. So B, 5. What happens? So on a B, if I'm in state 5, I stay in state 5, right? But there's no other states. Then I apply the epsilon closure onto that set of states, which just has 5 in it. It still contains 5. Nothing else, though. Have I discovered any new states that I have not accounted for with a row? Now, I've got them all. But there's one thing I did not account for quite yet. What are the final states? Well, as per our discussion, as long as it's a subset that contains at least one of the final states of the epsilon NFA, we're good. So, notice that this one has a 5 in it, that has a 5, this has a 5. So, this is the final state, that's the final state, this is the final state. And then once you're done with this, you're welcome to relabel the states if you would like, rather than working with subsets. But let me draw the resulting DFA. So let's look at the resulting DFA. So we're going to have a kind of beefy start state. It's going to have 0, 1, 2, 3, 5 as a subset. So our start state is right here. It's technically a final state, so I'm going to double circle it. On A or B, it goes to state 4, 5. Which again is another final state. Then it can fork off in 2 directions from 4, 5. It can go to this trap state or dead state, or it could go to this new state. So on B, it can go to the state that corresponds to the subset with just state 5 of the epsilon NFA in it, which is again is another final state. And if it keeps reading B's, it stays in this state. However, we have our dead state, which on A's and B's, it stays in this dead state. Goes there if you read an A here, and it goes to the dead state if you read an A here. But that's not a final state. So this is the resulting DFA from the lazy subset construction applied to this epsilon NFA. So please note that the main differences are when you come up with the start state, it has to be that it's the epsilon closure of whatever that state would be, as opposed to before it would just be the set containing the start state of the epsilon of the NFA. Next, final states, same concept. Contains one of the at least one final state. It's got to be one of the final states. Not much different. No. The main thing that is different, other than just the way the start state is defined, is how you determine each one of the transitions. It's 2 steps. The first step is exactly the same as it would be if if you apply the subset construction to an NFA, but it has a second step where you just apply the epsilon closure to that set of states before you put it in that cell. So that's just an extra step you have to do before you put it in the cell. And you might ask, Dan, why do you do that? It's because that's the definition of how it computes. So if you miss out that step, you're not working with an epsilon NFA anymore, you're working with just a vanilla NFA. And that's why that second step exists. So, because you need to have it where you allow it to go on those epsilon transitions to incorporate any states that it is able to reach via epsilon transitions. So, this brings me to an ultimate question. Do epsilon NFAs give us any more computing power, as in it recognizes more languages than a DFA? Well, let's talk about this now. So I'm going to give you a little sketch of where I'm going with this. So just to summarize where we were before, remember that we talked about this a little bit. Is that previously we had shown that if I give you an NFA N and has a language N, we can use the subset construction or its lazy counterpart to create a corresponding DFA D, where its language is L of D, where these two languages are in fact equal to each other, meaning that there's an equivalency between these two models. So for any DFA, I could construct an NFA, and for any NFA, I could construct a DFA. So there's an equivalency. Now, it should be not very surprising at this stage, given that I've given you a process that converts an epsilon NFA to a DFA. Its proof of correctness is very similar to the one that I did for the NFA to a DFA. That's why I'm not going to present its proof here, because the proof is nearly identical, just you have to incorporate the transition function and those couple little wrinkles that come with the epsilon NFA's definition. Other than that, the argument is the exact same. So that's why I'm not going to prove it here. But it's also worth noting that every DFA can be recast as an NFA, where its set of transitions always consists of one state, right? So technically speaking, there's a very trivial way of going from a DFA to an epsilon NFA, because every NFA is an epsilon NFA. The only technicality you have to watch out for is that when you define it akin to our transition table over there, is that I need to define transitions on epsilon, all of them, appropriately. So if I have it where you're allowed to have these epsilon transitions, well, what do you do with them? Well, they don't go anywhere, right? So but that's the only technical detail. Other than that, you're just dealing with a vanilla NFA again, right? And you just apply the basis for the NFA definition for when you read an empty string, right? So that brings me to the question. Okay, so now we know that if I give you a DFA, I can give you a resulting epsilon NFA. So I could may as well just put this here. And now you can go from the epsilon NFA to the DFA as per the lazy subset construction, or just the subset construction more broadly. You would just apply the epsilon closure for the second step as per the subset construction before. You can go from here to there. So that gives me the point of describing the next theorem to you. So, similar to before, so that's doing a lot of heavy lifting here, but similar to before, epsilon NFAs are equivalent to DFAs. They recognize regular languages. So I'm not going to present the full proofs to you, but like I said, the arguments present are nearly identical. You just have to add in the couple wrinkles for defining things such as the epsilon-transitions, and in the part from the subset construction, you would just add in the parts involving the new start state and the fact that you have it also where you employ the epsilon closure. Other than that, the argument's the exact same. So anyways, this gives us our theorem here, the big theorem for today. So a language L is recognized by a DFA if and only if L is recognized by an epsilon NFA. So that means that the epsilon NFA does not give you more ability to recognize other languages other than what we had for the DFAs, akin to the NFAs. It just gives us a richer feature set for how we can design these machines. So are there any questions? So as I mentioned, previously I had proven for NFAs to DFAs the equivalency. The argument is nearly identical. If you want to see a proof of this, please let me know and I can direct you to an appropriate source for that. If not, I can easily write it up for you if you're curious about it. I think one thing I'll do before we go today, we're going to do one more example. I think it's a good idea we do another example. So we have that epsilon NFA that would read decimal numbers. I was thinking maybe we can apply the lazy subset construction to it. So I was thinking that might be a good place for us to go with this. So let me draw out that. But if you have any questions or you want to join in the fun, come on down. Just going to close one thing here on my end. It's also a good opportunity for us to do this a little quicker and deal with a little bit more of a complex example. But again, like I said, this is a fairly classic example, and I encourage you to think about how you can read decimal numbers with other formats too. This one's just simply string dot another string. It's with some optional plus or minus. It doesn't have to be that way, right? It could be that you would like it so it always is negative or always positive, and you had a dot, then you can have something after it. I might want to have it where it has something and then a dot, or anything dot something, right? So let me just make sure I got this in front of me. Let's let me just get our epsilon NFA up, and then this will help us. So our start state, remember we had it where it had an optional plus or minus. Then on Q1, we read 0, 1, all the way up to 9. Then it had a decimal that you would read. Then for Q2, after that, it would have to read at least one digit. Q3, it's allowed to read more digits. And freely after that, it's welcome to go to the final state by an epsilon transition. Then we had an alternate path where we permitted it to have a number before the decimal And then we forced it to have a decimal if you were to take this pathway. So, let me see. I think I got everything here. Yes. So before I get into everything here, we're just going to carefully go through this. I don't see any questions, so I think we'll go through this carefully. And I think this will be a perfect place for us to stop for today. Because when I come back next time, we'll see what we're going to do next. We might do some more discrete math. That's the dreaded M word. It's a good old time, though. Do more discrete mathematics, or we might do more. We might start talking about regular expressions. If not, we might talk about this concept of languages that may exist outside of the regular ones. We'll see. If you have any suggestions or you'd prefer to see one of these, let me know in the chat or the comments. I'd like to hear from you. Okay. So previously we had described the lazy subset construction for taking any epsilon NFA to construct a corresponding DFA that accepts the same language or recognizes the same language, however you'd like to put it. But previously we had seen this example of an epsilon NFA. I'm going to show you how you can apply the lazy subset construction to take this epsilon NFA to produce a corresponding deterministic finite automaton. That is, it will recognize the same set of languages. So we're going to be walking through the steps of the lazy subset construction with this somewhat more, it's a classic example, but it's also a little bit more complicated than our first example. So what I'm going to do is I'm going to make a table. I usually recommend you use a table to carry out this process. It makes it a little easier for you to keep track of things. So notice that I really only have a certain number of labels here. I have plus, I have a minus, then I have a whole bunch of transitions where they're just 0, 1, 2, 3, 4, all the way up to 9. Each of those would technically have their own column, but because they all are the exact same in these, I'm just going to truncate it into a single column because all of their transitions would be the exact same. There's nothing interesting by adding separate columns for these. So I'll have that. We'll have dot, plus, and minus. So what is the start state or label for the start state of our DFA? What would it be? Well, the start state of this epsilon NFA is Q0, right? So how do I determine the start state of our DFA? Well, remember, the way we do this is we apply the epsilon closure to the start state of the epsilon NFA. But what's this? Well, it would be Q0. Remember, Q0 by definition is a part of the set. That is a result of the epsilon closure. But also notice there's an epsilon transition from Q0 to Q1, but there's no other ones leaving from Q1. So the start state would be the subset Q0, Q1. And that's where we're going to naturally start for the lazy subset construction. So let's now proceed. So on the 0 through 9, remember all of these are technically different input symbols. So what can happen? Well, in Q0, there are no 0 through 9, right? So there's no transitions for there. There's nothing interesting going on there. Q1. Well, it could stay in Q1 or it could go to, whoops, we need Q4 here. Or it goes to Q4. I knew I was going to miss something in that diagram. Q4. So we got Q1, we got Q4, right? Those are the two we could go to on these specific input symbols. So if you apply the epsilon closure to the set Q1, Q4, are there any new states that we encounter? No, right? So we have Q1, Q4. How about now on the dot? Well, on the dot, we could go from, notice there's no transitions out of Q0 on dot. There is one on Q1, goes to Q2. So that's the only set we have. But notice there's no epsilon transitions out of Q2. So the epsilon closure doesn't change this set. It's the same set. How about plus and minus? Well, this would be associated with Q0, right? Because plus minus ain't anywhere else here. So Q0 could go to Q1 on plus or minus. So that means that you're going to end up with Q1, but notice there's no, there are no epsilon transitions out of Q1. So the epsilon closure of the set containing Q1 is just the set containing Q1. So now I'm going to consider the next state we had discovered. So I'm going to do it by newest one that I run into. So the first one I ran into was this one. So that's the one we're going to consider next. So this is the first one that we had discovered. So next, let's consider this subset, Q1, Q4. Let's go through the same process. Okay, Q1, Q4. Q1 and Q4. If I read 0 through 9, it can stay in Q1, right? But it doesn't go anywhere out of Q4. In fact, there's nothing that it transitions on for there. So it's just Q1. But notice it can stay in Q1, but it can go to Q4. So it has both of those two there. So it's actually the same exact subset, Q1, Q4. Because when I apply the epsilon closure, there are no epsilon transitions out of these two states, right? So I just read it like that. Next, what do we got here for the dot? So I have Q1, Q4. So on Q1, I can go to Q2 on the dot. Q4 could go to Q3 on the dot, right? So what can happen then? What can happen then? Well, notice here that it could go to Q3, but there's an epsilon transition that takes me from Q3 to Q5. So that's also going to be a part of this resulting set. That's the part of the second step. So I have Q2, because I can go to Q2 on the dot from Q1. So I got Q2. Then I have Q3. That's from Q4 to go to Q3 on the dot. But notice that if I apply the epsilon closure to Q2, Q3, I end up with Q2, Q3, Q5. So now I have that subset. So I found another one. Plus or minus, nothing interesting going on here. In fact, all of the rest of these will always have it where these are going to be the empty set. So next, let's consider the next state we've discovered. So the next newest one, so this would be the second one we discovered. We're going to consider Q2. So the subset that consists of state Q2. Excellent, excellent. Let's consider now what happens here. So if it's in Q2, it reads 0 through any one of 0 through 9. It goes to Q3, right? But notice that in the second step, I apply the epsilon closure. So it's Q3 and Q5 because Q3 is a part of the epsilon closure of the set containing Q3. And it also includes Q5 because there's a transition right there. So I've got Q3, Q5. Notice there's no dot leaving Q2. So that's not terribly surprising. So it's going to be empty, empty, empty. Because plus and minus, there's nothing going out with plus or minus from Q2. Now, let's consider the next state we had discovered. So this was the first one, this is the second one, this is the third one. So next, we have Q1. So Q1, 0, 1, 2, 3, all the way up to 9. I read it, I could stay in here, or I can go to Q4, right? Epsilon closure of that is the exact same set. How about on dot? Where does it go for Q1? Well, we only have one state here. So On dot, it goes to Q2. What's the epsilon closure of the set that contains Q2? It's just Q2, right? In that one set. It doesn't change. Then nothing going on with plus or minus. Not terribly surprising. Let's go to the next one. So we've accounted. So if it helps a little bit, maybe like make little dots to help you. Just remember. So I got Q2. I got Q1. So what's the next one I have? Q1, Q4 I already got. This one here. This Q2, Q3, Q5 subset. Remember, these are just labels for the DFA. Got Q2, Q3, Q5. So now, let's figure out what's going to happen. So remember, I go through 0 through 9. Q2 could go to Q3. Q3 could stay in Q3, right? Q5 has nothing, right? However, the epsilon closure of Q3 would be what? Q3, Q5, right? Q3, Q5. Nothing on dot. So there's no transitions out on these states for dot. So we got nothing, nothing, nothing. I got nothing for the rest of the row. Nothing. So next. So we accounted for this one. We got Q3, Q5. That's the next one we got. I think this is, so far this is the only thing we have left, is just Q3, Q5. Okay, Q3, Q5. It can stay in Q3 on 0 through 9. Any one of those symbols, it'll stay in Q3. Q5, there's no transitions out of there. However, the epsilon closure of Q3 is what? It's Q3, Q5. So it's the set containing those two states. The exact same two. There's nothing on dot. There's nothing on plus. There's nothing on minus. Now, we're not quite done yet. We still have to label the final or accepting states. Which ones are the final or accepting states? Which ones? Which ones? Well, it's the ones that contain what? Q5, right? Because Q5 is the final state of the epsilon NFA. This isn't any different than what we had previously when we considered NFAs. Well, as a Q5, that is a Q5. None of the other ones have Q5 in them. So these are our accepting states. So let's draw out what the resulting DFA looks like. Let's see what the transition diagram looks like. So watch me butcher this. Here we go. So here we go. So we're going to have Q0, Q1. Now, for Q0, Q1, it can go to one of 3 different states. There's the subset that consists of just Q1. There's the subset that consists of just Q2. And there's another subset that consists of Q4. And yes, I did carefully lay these out in advance so that the picture would look a little nicer. So on dot, it goes to the subset Q2. On plus or minus, it goes to subset Q1. And then for 0 through 9, it goes to that subset, the one Q1, Q4. Now, let's consider Q1, Q4 next. It has 2 different states. One, it could stay right exactly where it is on 0 through 9. Or it could go to a different state. This Q2, Q3, Q5. Which this is indeed a final state. So it can go there on what symbol? Dot. So we've accounted for, have we accounted for everything? Have we actually accounted for everything? There's technically a subset I didn't label, right? Where is it? That one, right? This is actually also a state in this DFA. But, just to make it a little less scary looking, so I must stress that when you're done this process, because remember, this is another subset we had. Technically speaking, it would go right between Q3 and Q5. But it looks like this. So there's going to be a dead state that all of these are going to go to, but just for the sake of convenience, I'm going to draw this as a DFA with dead states. So technically speaking, what I'm going to be drawing here is an NFA, but you can take it and transform it into a DFA by adding another state in that includes that one right there. And then what happens is you make transitions for all of those symbols for each respective state as per this transition table. So please take note of this small little detail. This is a matter of convenience, but technically speaking, this row would be a resulting row in the subset construction, because it is a subset that is reachable from the start state. But I'm just going to omit it from my transition diagram. That's actually why I wanted to draw this out with you, so that way you could be convinced that that actually we weren't actually done this process quite yet. Technically speaking, this row would have gone between these two, because we've discovered the dead state before Q3, Q5. But it doesn't make any difference, because technically speaking, we could have anyway evaluated one of these before that. But the point I'm getting at is that this is just a matter of convenience. I'm drawing it as an NFA, although technically speaking, you would have one more state here for the subset that is the empty set. And it would have arrows all going out towards it for those appropriate transitions. So let's continue now. So next, we've counted for let's look at I believe it's Q2 next we got to look at. Q2 has Q3, Q5. Q3, Q5. So Q3, Q5, it is technically a final state because it has Q5 in there as one part of the subset. And it could stay in here upon reading 0 through 9, as per what we've noted right here. But let's continue with Q2. So Q2, there's nothing else, right? It would just have that dead state that it would transition to on all the other cases, right? So next, let us consider Q1. So Q1, well, on Q1, it goes Q1, Q4 for 0 through 9, right? And it goes to the dot. On dot, it goes to Q2, right? It goes to this one right here. All the others would transition to a dead state. As I said already, I've omitted that from this drawing here. So technically speaking, if you literally interpret what I'm going to draw here, it is an NFA. But you can make it a DFA if you add in this dead state, the one corresponding to this row's label. So now let's consider Q2, Q3, Q5. So it could transition the Q3, Q5 on 0 through 9. Nothing else though, and it will go to the dead state in all the other cases. Next, we got Q3, Q5. Stays in Q3, Q5. I already accounted for that. And then, yeah, naturally you would have a dead state out over here, where on all the other symbols you would transition to this dead state. It would never escape the dead state. But yeah, this is the resulting DFA with dead states. So this is an example of applying the lazy subset construction. This would be the resulting DFA's transition table. And this is a transition diagram where I've omitted the dead states, so-called the DFA with dead states. So any questions? Any comments? Now's a good time to bug me if you want to talk about the subset construction. But remember, the big picture look of this whole thing is that if I give you a DFA, I can give you an NFA. Likewise, I could do the opposite. Likewise, every NFA is, in fact, an epsilon NFA. It's all just a special kind of epsilon NFA. If you use epsilon closures appropriately, you can construct a corresponding NFA, but I don't think it's terribly interesting, so I'm not really going to talk so much about it. However, you can go from an epsilon NFA to a DFA, and vice versa too. So it's actually a relationship all three of these have. You could go between any one of these three. So all of these recognize regular languages. But no, are there any questions? Any questions at all? Because that's everything I got to cover for today. I thought I would go for something a little shorter here today because it is Valentine's Day. I know people got all sorts of fun things they want to do for their day. So I thought it'd be a great idea we see this variant of an NFA. That way we could see that you can actually buff up the NFA with more features and you don't actually lose, like, for better or for worse, you don't gain any computational power by doing this, other than describing the machine that you would like to recognize the language becomes easier. So the whole point is that the epsilon NFA gives you a rich set of features that allow you to detect things like keywords a little easier, and it gives you more options, so optional features such as in our example here. Actually, this is technically my example. This is a classic example where what you could do is you can introduce optional features such as having an optional plus or minus. Or if you're done reading zeros, any additional digits, you can accept at any time, as long as you're done reading symbols. So you could use these for all sorts of fun little designs, but the point is that there always will be a DFA that you can construct from one of these finite automata. But yeah, no, it doesn't appear there's any questions, so I think this is the perfect place for us to stop for today. So I want to wish you, your family, your friends, your special loved ones, a wonderful Valentine's Day, and have yourself a beautiful day. If you want to get access to the notes from today's lecture, please consider supporting on Patreon at patreon.com/pagewizard. At the supporter access tier and above, there's all sorts of rewards, many that are really exciting. You even get access to our Discord server. You get access to these notes from today, and they also include the example we've just talked about here. So other than that, please tell your friends to come join the fun. And I'll be back probably on Thursday. We'll be playing, I believe we're going to be playing either Chrono Trigger or Mega Man 11. I'm pretty sure it's Chrono Trigger. So I'll say thank you so much and have yourself a beautiful day. I'll see you later.